Our topic today is equivalence relations and partitions. I've actually already given an example of a partition. Now I'm going to assume everyone is familiar with the language and notation of elementary set theory, what we call naive set theory. Start with a set S. What I've written here is a way of splitting up the set S into a bunch of disjoint subsets, S1, S2 up to Sn. Their union is all of S, and no two of them overlap. So in place of the usual cup symbol for union, I can use this square cup symbol to emphasize that it's a union, but with no two of the parts overlapping. So we usually assume that the parts, which are the SIs, are non-empty subsets. These subsets are called parts, hence partition. In this case, I'll call the set of parts a partition of S. And I write script S for this partition of the normal S. Notice I'm using S for the original set and script S for the partition. These are not the same thing. S is some set and script S is a collection of subsets of S, hence a set of sets. The word partition, which I've used as a noun, can also be used as a verb, and we say that we have partitioned the set S into n parts, or that these n parts partition the set S. That's a verb. For example, our university has a set S of 11,950 students. These students come from 93 countries. I can partition the student body according to nationality. This gives 93 parts. Let's say S1 is a subset consisting of students from the USA, S2 is a set of students from France, S3, the set of students from Pakistan, and up to S93. Okay, so that's the set of students from South Korea. So there are 93 parts in the partition. Script S has 93 elements, each of which is in turn a set of students. And the union of these is the original set S, the entire student body. So there's a big difference between S and script S. Partitions don't have to be finite, and the parts themselves don't need to be finite. And for us, they often won't be. So I can't index the parts using indices 1, 2, 3 up to n. This changes the notation just a little bit, but the concept is the same. Now, a partition of S is a collection, script S. It's a collection of subsets of S, usually non-empty subsets, such that any two of the parts are disjoint, which means they don't overlap. So they're mutually disjoint, we say, and their union is all of S. The usual cup symbol can be used to express their union, but we can also use this square cup symbol to emphasize this is a disjoint union in which the parts are mutually disjoint. This gives us a partition of the set S. It's often convenient to index the parts of the partition. When there are only finitely many parts, we could index them using indices 1, 2, 3 up to n, if there are n parts. But in general, any set, call it script I, this is a script letter I, can be used as a set of indices. Any set that has the right size can be used to index or to label the parts of the partition. So we summarize. Script S is the collection of parts, the set of parts. It's the set whose elements are the SIs, as the index I ranges over the index set, script I. The original set S is the union, the disjoint union of the parts. So I can use the square cup symbol if I want to emphasize this fact. S is the union of the parts of the partition. I can write S as the union of the SIs as the index I ranges over the index set, script I. Here is a very nice and pretty rich example with a partition that arises in a very natural way. So take the Euclidean plane, you know what that is. It's R2, the usual xy plane with real coordinates x and y. I'm going to let L be the set of all lines in the plane, all the lines of the plane. The set of lines is naturally partitioned according to the slopes of the lines. So for each real number m, I have the set of lines of slope m, which I write as L sub m. So L sub m is the set of all lines having an equation of the form y equals mx plus a constant, some constant b. By varying the constant b, you get all the lines of a fixed slope m. Well, we also have the vertical lines. We'll just say that the vertical lines have infinite slope. So I'll write L sub infinity for the set of vertical lines. These are the lines having an equation of the form x equals constant, where a is some real constant. Now, I have a partition of the set of all lines in the plane. How can I index these lines? Well, I'll use this index set. Script I is the real numbers union one extra symbol that I'll write as infinity. Moreover, each of my sets, L sub I, is a partition of the set of points of the plane. So each parallel class of lines partitions the points of the plane. And then I have a partition of the set of lines. So I'm partitioning the points in many different ways, and I'm partitioning the lines in one way. So it's a pretty amazing example. It's like a partition full of partitions. The set script L is a partition of L, just as I started by partitioning the set of all lines into parallel classes. And then each Li itself is a partition of the point set of the plane. It's worth pausing the video here to sort out what we're saying and see, yes, this is an amazingly rich example, or bunch of examples. Now, we want to move from partitions to the notion of equivalence relations. But let's first talk about relations. S is any set. A relation on S is a property of certain pairs of elements of S, meaning that, for each pair, A, B, some pairs have this relation and others don't. The relation either holds or doesn't. And since we're taking pairs of elements of S and defining relations on pairs, then this is what we call a binary relation. So we want to emphasize here the kind of relation. Sometimes there are entuples that we define relations on. Here we're just going to take pairs, so all our relations will be binary relations. I want to emphasize that it's not a property applied to individual elements of S. It only makes sense to define it for pairs of elements of S. Some pairs have it and some don't. For each pair of elements A, B, either they're in the relationship or not, I can write A tilde B. If they are related, I can write A not tilde B if they're not related. So a tilde with a slash through it. Notice this is quite different from a binary operation. Applying a binary operation to A and B would give you an answer which is an element of the original set. But when you're talking about a relation, you don't get an element of S. You'd get just a yes-no answer. Yes, they're related, or no, they're not related. Now let's talk about some examples, starting with a set of people, a set S, maybe the set of all students in our university. One relation is that of knowing each other. So of one person knowing another. So giving people A and B, either A knows B or A does not know B. Let's just make it one or the other for simplicity. Another example would be the relation of being taller than. So for two people, A and B, you say either A is taller than B or not. Other relations to consider would be owes money to, or is a sibling of, or lives 100 miles away from, etc. Many different kinds of relations you can imagine. Now let's look at possible relations on this set of real numbers. One relation is equality. Another is the less than relation. It's not an operation, it's a relation. Another is the less than or equal relation. Another is having distance 2 on the real line. These are just examples of a vast number of the relations available. Now, a binary relation on a set S is really the same thing as a subset of the ordered pairs. That's a subset of the Cartesian product S with itself. So the Cartesian product of S with itself is the set of all ordered pairs AB, with A and B being elements of S. So in an ordered pair, you have a first element A and a second element B in that pair, and the order matters. So we're talking about ordered pairs, set of all pairs. It's like taking points in a plane where you take XY coordinates. So you can take, for each relation, you can look at a subset of S cross S, consisting of just those pairs that are in the relation. That gives a subset of S cross S. This subset of S cross S exactly tells you the relation. It's just giving you exactly the same information. Or the other way around, if we have a subset of the ordered pairs on S, then what we have is a relation. We say A is related to B if the ordered pair AB is in our subset. So in this way, every relation can be viewed as a subset of the Cartesian product of the set with itself. When you take a relation on the real numbers, then you can think of that as a subset of R cross R. In other words, a subset of R2. It's a subset of the Euclidean plane. Now, the equality relation gives the line y equals x. That's a particular subset. It happens to be a graph of a function. The less than relation is the set of, it's not a function, it's the set of all points which are above the line y equals x. So that's a relation is something more general than a function. Now, there are many relations. Some are more interesting than others, especially for us. Let's talk about some interesting possible properties a relation might have. The first one is reflexive. You say a relation is reflexive if every element of the set is related to itself under the chosen relation. You say that the relation is symmetric if the order doesn't really matter. That is, whenever little s is related to t, then t is related to s. And then you say a relation is transitive if every time you have s related to t and t related to u, then you also have s related to u. And if a relation has all three of these properties, then we call it an equivalence relation. For example, if you're on the set of real numbers, the less than relation is transitive. If s is less than t and t is less than u, then s is less than u. But the less than relation is not reflexive. Elements are not less than themselves, and it's not symmetric. So if s is less than t, you don't have t less than s, it's not symmetric. So I guess it has one of the three properties. So the less than relation is not an equivalence relation. The less than or equal to relation is transitive as before. It's also reflexive because each element is less than or equal to itself, but it's still not symmetric. So less than or equal to is still not an equivalence relation. On any set, equality is always an equivalence relation. That's a pretty trivial example of an equivalence relation. Let's look for other examples. Let's look at a set of people. And if you think of knowing somebody as being symmetric, which maybe it is, so if A knows B, does B know A? Maybe you can assume that. I think it's probably a good assumption to say that each person knows him or herself, but it's probably not a good assumption to say it's transitive. So if A knows B and B knows C, does it follow that A knows C? Not in most cases. So that's not an equivalence relation. Here's an example of an equivalence relation, certainly less trivial than my first example. So on any set of people, the relation of having the same age in years is an equivalence relation. If A and B have the same age and B and C have the same age, then A and C have the same age. That's transitivity, and you can easily see reflexivity and symmetry. So That's an equivalence relation. Here's a very important example. Take any two sets, A and B. We'll say that A and B are equivalent in size if they have the same number of elements. What does that mean? Well, cardinality. We're going to spend a future video talking about cardinality. But what it means is that there's a bijection between the two sets. If you have a bijection between A and B, that's a way of comparing their size, saying they have the same size. And this is an equivalence relation for sets. So far, I've been talking about partitions and equivalence relations as if they were two separate topics, but actually, these are just two different ways of talking about the same thing, the very same thing. Now, if you specify an equivalence relation on a set S, this determines a partition of S. The other way around, if you give me a partition of S, this determines an equivalence relation on S. How does this work? Well, we'll start with an equivalence relation on a set S, and I need to show you how this gives rise to a partition. So we talk about the equivalence class of each element. So you have an element A of S. Then its equivalence class is the set of all elements that are related to it, the set of all elements that are equivalent to it. That's a subset of your set. Now, my notation for that class has brackets around A. So it's a set, and the way you define it depends on which relation. So if you need to specify that, if you need to clarify, then put a subscript on your brackets. Note that for B to be in the equivalence class of A means the same as B being related to A, and that's the same thing as A and B defining the same equivalence class. And this, by the way, is the same thing as the two classes intersect in at least one element. They're not disjoint. If they're not disjoint, they have to be equal. So these are equivalent ways to say the same thing, and if you check all these properties, then it follows pretty quickly that the set of equivalence classes forms a partition. Two equivalence classes are either disjoint or they're equal, and they cover the entire set. So this gives you a partition of the set. From an equivalence relation, you get a partition. Now for a set S with a relation tilde, you can write S mod tilde to be a shorthand way of talking about the partition that you get from this. And the other way around, if you start with a partition of S, then that gives you back an equivalence relation on S. How is it defined? Well, the relation would be that two elements are equivalent if and only if they lie in the same part of the partition. Either lie in the same part or in different parts. So that's the distinction that defines your relation. It's an equivalence relation. There's a lot of formalism to think about. Let's return to our early example of the Euclidean plane. Let L be the set of all lines in the Euclidean plane. Now I defined a partition of the lines. Let me rephrase everything I did in the language of equivalence relations. So the natural relation to talk about here is parallelism. So given two lines, L and M, little l and little m, you say they're parallel if they have the same slope. Now I have to clarify here that I want to say a line is parallel to itself, otherwise it won't be reflexive. Well, a line does have the same slope as itself, so I guess by my definition, yes, that works. A line is parallel to itself. And notice if L is parallel to M and M is parallel to N, then L is parallel to N. So yes, this is an equivalence relation on the set of lines of the plane. Now the equivalence classes are exactly the parallel classes, which I defined before. For each slope, you have a parallel class, which is, a member of the partition, a part of the partition. The equivalence class of each line is the parallel class. It's the set of all lines having the same slope. My index set for the parallel classes, the equivalence classes, is naturally the real numbers together with one extra symbol that I'll call infinity. So we get a partition to practice our notation. It's the set of lines mod the parallelism relation. I could call it script L, but it's also ordinary L. mod parallelism. It's a set of parallel classes. As another example, this is more numerical. So we partition the integers, the set of integers, into two parts, the evens and the odds. E is the set of even integers, O is the set of odd integers. By the way, even means a multiple of 2, and odd means one more than a multiple of 2. And we're just going down the number line and alternately coloring each number red or black, just like on a checkerboard, except it's a one-dimensional checkerboard. By the way, please, 0 is even. So this corresponds to the notion, the relation of congruence mod 2. That's an equivalence relation where we say A is congruent to B when their difference is an even number. By the way, we could discuss congruences for any modulus. Here I'm just taking mod 2 as an example. And since 2 is a fixed modulus, I won't keep saying mod 2. Congruence just means congruent mod 2. The two congruence classes for this relation, they're the congruence classes of integers mod 2 are the evens and the odds. The congruence class of 0 is E, and the congruence class of 1 is O. These are the only two equivalence classes, the only two congruence classes. For example, the congruence class of 7, well, that's just the odds. That's the same as the class of 1. I've already listed that in my classes, so I don't need to list it twice. So the resulting partition just has two parts. Now there are many ways, many different notations for this partition. So in my general notation, I can write the set of integers mod congruence. Congruence mod 2. And this gives us the parts, which are two parts, the evens and the odds. This is the same thing as the integers mod the evens, and I can write it that way. It's also F2, it's the field with two elements, the field of order 2. There's so many ways to write this thing. Surely enough ways to please everybody. I mean, no need to try to come up with other names for this field than the ones we've already got. Why do we care about doing this? Why do we care about equivalence relations, aka partitions? And this is very important. I mean, why do we do this? This is the question, right? It's because this is a goldmine of new and interesting structures. It allows us to construct new things from old. It's a very prolific way to find new and interesting things. You know, just so many things that you could list that are constructed basically in this very way. Here's one. You can start with the integers and take mod 2. It's mod the equivalence relation of congruence mod 2. And then you get the field of order 2. So you might have already known about the field of order 2, but if you didn't, then you could discover it or construct it this way by starting with an equivalence relation on the integers. Here's another very important thing. You know, if you take the set of lines in the Euclidean plane and you just identify them if they're parallel, then what you get is something called the real projective line. This set R with one extra element called infinity. It's not just some crazy mistake or happenstance that this came out. This is a very crucial example in mathematics. It's called the real projective line. We took the parallelism relation on the lines of the Euclidean plane. The partition is the partition given by the set of slopes, but as soon as you just take the set of parallel classes, then that it really is just the same as talking about the real numbers, union, an extra point, infinity. This is actually a natural thing. Of course, it's more topology or geometry. Now it's not algebra anymore. Now here's another similar thing. You could do planes in R3. Then what do you get? Well, you take, again, parallelism. You know what parallel planes are. And if you take the parallel classes, they correspond to the points of what's called the real projective plane. It's got some interesting geometry, some interesting topology, not a subject to really spend time on here, but here's another bit of topology. You can take a rectangle and then put an equivalence relation on it to get all kinds of things, starting with a very humble rectangle, Euclidean rectangle. You can impose an equivalence relation and get a Mobius strip. You can get a Klein bottle. You can get a torus, and so on, all kinds of new examples starting from something more basic. And in topology, there are many structures that can be difficult to understand or visualize directly, but the best way to really get at them and understand them and prove things about them is they have a straightforward construction as a quotient of some easier structure, which started by modding out by an equivalence relation. In a sense, this process lies behind most constructions. It definitely lies behind the actual construction of the real number system. It lies behind the construction of the rational numbers. Rational numbers come from fractions, but you have to talk about equivalent fractions to get there, and that means equivalence classes. It's buried in the construction. The construction of rational numbers from the integers, the constructions of the integers from the natural numbers, even the construction of natural numbers from sets, all of these use equivalence relations. And by the way, the construction of complex numbers from the reals, depending on your perspective, is maybe best understood using equivalence relations. This idea is just a gold mine for mathematicians because we look for new objects all the time. Now let's talk about how you would construct rational numbers from integers. And right now, you have a really good foundation, let's say, in the integers. You understand everything about the integers. Now, how do you explain to such a person what rational numbers are? And you cannot just say 1/3 is 1 divided by 3. What does that even mean? You can't do that, if you're in the world of integers. So you have to come up with a context in which that makes any sense at all. Now, if something hasn't been invented yet, how do you produce it? Well, you use set theoretic formalism with equivalence classes as your tool. The set we want to start with. If you know the integers and you know set theory, then you can talk about this set S, which is the ordered pairs of integers, in which B is not 0. So that's a subset of Z cross Z. And you define a relation on this set. It turns out to be an equivalence relation. So you say that 2 points of this set are equivalent if AD equals BC. So it's like cross-multiplying. So that defines a relation. And then it's not hard to show this is an equivalence relation. You should check this. It's an exercise and it's not hard. Very instructive. And if you have an equivalence relation, you can talk about the equivalence classes. You use a shorthand. Rather than bracket parenthesis AB, you just write A over B. And that just is a new and shorter name for the equivalence class. For example, if you're struggling to define 1/3, now I can say what it is. It's the equivalence class of the pair 1, 3. So it comes out to be just the set of all pairs of the form A, 3A. So the second number is 3 times the first number. That's the equivalence class. The notion of equivalent fractions is really just a special case of the more general notion of an equivalence relation or equivalence class. Now this partition, which is the set of equivalence classes, could be denoted as the set S mod our relation. We give it, again, a shorter name. We just call it Q. Set of equivalence classes is called the set of rational numbers. Now you got to start defining the rest of the structure, like how does this become a field? Well, you can actually define addition and multiplication of fractions. And you know what the formulas should be, but then you've got to check that they actually work, meaning that you've got to check that these operations are well defined. And after that, you've got to show that they satisfy the properties to be a field. And beyond that, you want to show it's an ordered field. And then you want to show that it's an extension of the integers. So really the integers, which we started with, can be identified as a subset of this new larger set. So the integer a can be identified as the equivalence class a over 1. This allows you to develop everything you need to know about the rational numbers from the integers. If you have the idea of an equivalence relation, you can do that. This formalism uses, of course, stuff from set theory as well. So set theory is used in everything. So somehow, whatever way you talk about developing mathematics from scratch, you're going to want set theory or something equivalent to that, something equally powerful to prime the pump. Now, going from the rational numbers to the reals is a similar step to the one we just talked about. And, that's certainly not a topic for today.